In this work, we present Evetac, a new event-based optical tactile sensor for robotic manipulation. Evetac's design consists of an event-based camera capturing the deformation of a soft silicone gel. Illumination is provided by a white LED stripe surrounding the gel. The sensor is held together by a 3D printed housing, for which we open sourced the design files. All the other components are commercially available. Evetac returns sparse measurements at 1000 Hz and provides a resolution of 640 by 480 pixels. Thereby, the sensor offers both human-like temporal and spatial resolution. Every measurement contains a set of events visualized in black and white. When there are no changes in contact configuration, the sensor does not return any information. In benchmarking experiments, we compare Evetac and a standard RGB optical tactile sensor, GelSight Mini, in terms of data rate. Despite Evetac's significantly increased readout rate of 1000 Hz versus 25 Hz of the RGB optical tactile sensor, its sparse measurements result in only producing 2% of the data compared to the RGB optical tactile sensor. Evetac's raw output is sparse and solely contains local information. It is thus not possible to reconstruct the current global deformation of the gel given single measurements. However, since this information might be crucial, we present an algorithm for tracking the dots imprinted in the gel. We investigate two versions of the algorithm, a regularized version and an unregularized one. The video shows how the unregularized tracker in red loses track of some of the dots, while the proposed regularized version is more robust. This slowed-down video of the tactile interaction reveals that the unregularized dot tracker is prone to following the events triggered by the external object. After successfully benchmarking Evetac, we now investigate a more practically relevant task, slip detection. Contrary to prior work in event-based tactile sensing, we propose to learn slip detection and prediction models from labeled experimental data. The video illustrates the data collection process where, starting from a stable grasp, we open the gripper to cause slippage. When the black bar in between the external view and Evetac's measurements turns red, slip is detected by the classifier. We repeat this procedure for all 9 training objects. After having collected data and trained slip detection models, we integrate them into a real-time grasp control loop. Starting from making light contact with the objects, we attempt to lift and hold them stably. Whenever slip is detected, the grasp force is adjusted. This results in stably lifting and holding the objects. To verify that the initial procedure of making light contact with the object does not result in already applying sufficiently forces for lifting it, we repeat the same procedure with the controller turned off. As can be seen, this results in the object slipping through the fingers. We demonstrate the robustness and adaptiveness of the grasp controller by applying it on these 11 previously unseen testing objects. Across all experiments, we find high success rates of 92%. Finally, we evaluate the controller's robustness. As shown on the left, the controller can handle sideways grasps. In the middle, we show the controller's reactiveness. It can react to perturbing the grasp by dropping a 20-gram weight onto the grasp object. We can repeat the same procedure and even drop a 100-gram weight. We hope that our proposed open-source Evetac sensor, together with the touch processing algorithms and closed-loop grasping controller, will encourage further research in the direction of event-based tactile sensing and contribute to the efforts for achieving the still unparalleled human manipulation capabilities.